This is another video about Grblgru Lathe. This time I focused on using it for working metal. I am not a person skilled in metalwork. This is the opening screen of Grblgru Lathe. I usually like to move the cutter over closer to the chuck simply because it looks pretty. I'm going to open a project. In this case I want to create a M10 thread. I start with some rod stock. In this case it was a little bit too big. I did a rough turning down to a level where I could get an accurate reading. By opening the DXF file, a job is automatically created. You can see the parameters there on the left, and they're consistent with what I often do. Probably too conservative. The top cuts are on the metal and the bottom cuts are when it's being retracted. Going back to the main screen, I position the cutter at the right hand edge. I usually want tailstock support because you get a better cut that way. I enter the diameter that I had measured with calipers, run a test program to see what it's going to do. In this case I was flipping back and forth between high speed and not accelerated. And this should take my roughly 12 millimeter blank down to 10 millimeters. I exit that little program. I take it over to the shop. My starting diameter is 12.45 millimeters. A little oil because that helps everything. The lathe is running not too quickly, perhaps 1300 RPM. It's just a little lathe. And I start the program. I won't be speeding up any of these cuts so that you can see how it's done in real time. This is the slowest setting that Grblgru defaults to. I could easily speed all this up. This is mild steel. I've got a little bit of a point drilled into the right hand end for tailstock support. Even though the machine is moving the axes slowly, this is faster than I can do it, so it suits me fine. I'm in no hurry. I just want it done accurately. I will change back and forth between a powered chuck and a chuck controlled with a stepper motor. Naturally, I take the stepper motor belt off when it's not in use, because if you turned it under power you'd probably fry your electronics. Stepper motors are wonderful little generators. This depth of cut is very conservative at 0.2 millimeters. There's lots of time to add some lubrication or watch out for crashes, anything like that. I don't do enough metal work that it comes as second nature, that's for sure. I put in usually about a 5 millimeter retraction because there's a lot of play in my axis handles. That backlash is expected whenever you're dealing with screws, and the software I'm using, in this case Grblgru, can be adjusted for the backlash. There's a simple test routine that can be done, and since I have a inexpensive metal DRO, I can read the values off that directly and enter them into my Grblgru profile. As a result, the control board automatically adjusts for backlash in both the X and Z axes. And that little program has finished. My blank is prepared. So here's the blank program. I'm erasing that with the big red X at the top. I'm going into the 2D templates. There's one called threading, and this will generate a DXF file that Grblgru can use. You can see the threads already there. That's not what I want. I want a 10mm thread by 1.5mm pitch, and I want it about 15mm long. Now this has created a DXF, but it has not yet created a job. So you go to the right-hand screen, right-click, go down to Jobs, and select Threading. Now it calls up the threading routine. I can double-check the parameters. This one will do 6 passes. I do want a retraction, and I definitely want to use flank turning. The alternative is radius, but flank is much easier on my little 3 Newton-meter stepper motor that's driving the C axis. In this case, it cuts primarily on the left side of the cutter. I can preview this. I put in the correct diameter that I just milled my piece down to. And clicking on a number above has it recalculate all the G-code for the narrower diameter. And you can see this is going according to plan. The tip of the cutter will gradually cut a little bit deeper and a little bit further to the left each time, on the left flank of the cutter, obviously. I found that the radial cutting feature cuts too deeply, and my little stepper won't deal with that. This is quite a coarse thread that I'm doing. Obviously finer threads are much easier to cut. But I thought I'd like to try a 1.5mm pitch for a change. I'm going to stop this now because you get the idea. Reset everything back to 0, and we'll go to the shop. So here's a blank that I've prepared. I have a simple high-speed steel cutter that's cut fairly accurately to a 60-degree angle. I did not try to speed up the cutting, and I'll let this play out. Tailstock support definitely helps get a more accurate thread. This cutter has a flat top, so it's great for brass, but it really is not properly ground for steel. But I thought I'd demonstrate the simplest possible setup and see how well it works with Grblgru Lathe. As I mentioned before, this is a 3 Newton-meter stepper motor. It's a closed loop motor. I don't think I'd try this with an open loop stepper, because if you lost steps, then your thread would be very inaccurate. At this speed, there really is no rush to get anything done. I can pick off the chips with some pliers as I want to. I don't have to panic when it gets to the left-hand edge of where I want it threaded. It'll just stop. It's a very stress-free way of making threads, particularly for those of us that don't do this very often. Right now, Grblgru can make pretty much any metric thread. A little lubrication never hurts. It'll cut this thread in 6 passes, I believe. I'll break off the chips just so you can see a little bit better what's going on. As you see, the chip is really quite robust for a stepper motor. In the job settings, it's quite easy to speed up this process, but I'm in no rush since I'm in a more creative environment than a production environment. I just want it to get done right. There's a little tiny cut across you can see right there, and that's because I don't have enough backlash built into the job for my relatively sloppy lead screws on the x-axis. In the end, this doesn't matter because almost everything is cut away to get to the tips of the thread. Lots of pretty robust chips, and with the zooming in, you can see a little bit of the jaggedy cut along the shoulders of the thread. And once again, that doesn't really matter. You don't usually see threads up this close. It'll stop exactly where it's supposed to. No worrying, no fuss, no panic. Once again, this is a M10 by 1.5 millimeter pitch thread that's being cut 15 millimeters long. You can see the threads starting to sharpen up now. I found the tailstock definitely helps give a better end result, just like on a wood lathe. I should probably have cut some kind of landing groove on the left-hand edge of the threads, but then you couldn't see where the thread ended and how it ends at the same place every time. That's the beauty of using a closed loop stepper for these. It always knows where it is, and if it gets overloaded, it just stops. Thread tips are getting quite sharp now. I do have a proper carbide thread cutter, but I chose to use this high-speed steel just to show how little you can get away with. I think this is one last pass. It'll clean things up just a little bit. You can see some debris left over in the threads. I brushed that off with a stiff nylon or brass brush when I'm all done. And that is the end of cutting this M10 thread. However, the proof, they say, is in the pudding. So here's a nut. Threads on pretty well. And there's not too much play there. Seems like a pretty good thread, especially since I hand cut the 60°. Now I'm going to move on to a little bit more complicated shape. This is actually a part for my lathe. I previously saved this as a job. That's the GRU file. And this is a 3-step piece with 2 threaded sections meant to hold one of my change gears. Importing the file, I've already imported the DXF that I drew up in a CAD program. I double check the profile there to see if that's what I want. Once again, this is mild steel. Check the cutter. Go back to the live view. I position it right at the right hand edge and call that 0 and run the test profile. This cuts the right hand section down to 6 millimeters, the middle to 10 millimeters, and the left hand section to 12 millimeters. Once again, I didn't make any particular effort to speed anything up. I just left it with the default settings. Everybody's lathe is a little bit different, so you get to experiment and figure out what works best for your lathe. So that should run. We'll go off to the shop. Here's the same cutter setup. The lathe speed, once again, is about 12 or 1300 RPM. It only takes me about a minute to change between a motor-driven chuck and a stepper-driven chuck. I leave the motor belt hooked up when I attach the stepper motor, since it's powerful enough to turn both the motor and the workpiece. I've successfully threaded up to 12 millimeters. I haven't tried anything bigger than that as yet, simply because I haven't had a need to do so. Once again, before I started this program, I rough turned the outside of this mild steel down to something that was fairly uniform, measured that, and input that diameter into Grblgru. The more accurate you can get that, the more accurate your results are going to be. As you can see, the surface finish is pretty good. And that's also something I can't do very well, turning the Z-axis by hand. This does several roughing passes, then it'll do a couple of finishing passes. I think I'm probably not pushing my carbide cutters hard enough, actually. There's still lots of horsepower left in my motor. My depth of cut can easily be up to 0.5 millimeter or more. I'm backing just to show you how the hand wheels are twirling around there under the control of the stepper motors. Now I think it's going to start a finishing pass. A little bit finer chip coming off there. I think that's only 0.1 millimeters. Does a nice bevel there. And all of this I drew in a CAD program, in this case VCarve. I drew the entire profile and then sliced it in half long ways, with the right hand edge being at the origin. I showed how to do that in a different video. Sometimes I think lubrication doesn't help me at all. I seem to get a better finish when I'm cutting this shallow depth if I don't use any lubrication. To thread this, I'll use the same procedure as I just showed at the first part of this video. Pretty good surface finish, although that doesn't matter for threading. And here's a picture of the finished piece. Finally, I'll show something that's commonly done. I've prepared some stock again. In this case it's about 19 millimeters, and I want to cut a Morse taper 2 taper. So MT2 or MK2 as they say in Germany. Importing the DXF that I've previously drawn up according to the measurements I've found somewhere on the internet. Grblgru automatically creates a job, although I could erase that job and make my own job if I wanted to. I input the cutter, adjust the settings. I want some retraction to account for the backlash. The top cuts are on the metal and the bottom cuts are the retraction. Going back to the simulation, I set the tip of the cutter on the right hand edge of the piece of metal, enter the correct diameter for the rough turn piece, and start the simulation. And you can see the steps that it'll rough turn things, and then the final few passes to get the taper just right. I'll cut away to the workshop. In this case I ran the program that's slightly different than the one I just showed you, and you'll see I have a little bit of a problem when it gets near the end, but fortunately it didn't make any difference. On this first pass it looks like it's not cutting at all. I don't try to second guess how the computer algorithm figures out where to start cutting. Lathe speed is about the same, 12 or 1300 RPM. This is mild steel once again, since I don't actually need a Morse taper 2 tapered piece. And this is real time. I know I for one definitely can't cut taper as quickly as this thing can. And you notice there's no setup. I don't have a cross slide or a top slide to adjust, no angles to figure out. I figured all that out in CAD once for 5 different Morse tapers, and I never have to figure it out again. I'm taking fairly fine cuts once again, probably 0.2 millimeters, just because I'm very conservative. I'm still learning about this whole metal turning thing. I'll see if some lubrication can help. In this application, it's probably unnecessary, quite honestly. The tailstock support, I've noticed, does give me better results. In this case of making tapers, there's a fair amount of stick out from the chuck, so holding the other end really doesn't hurt anything. The majority of the roughing's done, and here's my little boo-boo. Pushes my tailstock back, so I get it out of the way. I ordinarily don't let it cut across the right-hand end of the piece. Although that is a useful feature for finishing the end of something like this. The flats that were done are gradually disappearing. My backlash compensation seems to be dialed in pretty close. A little bit of unnecessary lubrication, and this job is done. Here's a close-up of the surface finish right off the tool, and that does look pretty good. So I took this piece and put some Sharpie marker all over it and compared it to a commercially made Morse taper 2. I put my marked up piece I've just made in the tailstock, trying to find some shiny spots there. And I do this a few times just to get some idea of whether it's pretty accurate or not. And to my untrained eye, that does look pretty good. So I hope you enjoyed watching this video, showing some simple metal operations. Thanks for watching.